Hi, my name is Jamie DeYoung, and I created this video differentiating 1 over x by first principles for the course MAT135 at the University of Toronto. The goal of this video is to be able to differentiate 1 over x and other similar functions using first principles. I'm going to do a couple of examples and then leave you with some exercises for practice. So, the function that we have is f of x equals 1 divided by x, and we'd like to calculate the first derivative. But we want to do this using first principles. So what does that mean? Well, the limit definition of the derivative says that the derivative is equal to the limit as h goes to 0 of the function evaluated at x plus h minus the function evaluated at x divided by h. Now in this case, the function evaluated at x plus h is 1 divided by x plus h. And we're subtracting the function at x, 1 divided by x. And we divide all of this by h. Now before we actually calculate the limit, we'd like to simplify this fraction a little bit. And what we'll do is we'll try to write the numerator as a single fraction. So when we do this, we want to write them over a common denominator. So we'll get x divided by x times x plus h minus x plus h divided by the same thing, still all divided by h. So now we can write this as a single fraction. We'll get x minus x, this cancels out, so we'll be left with negative h divided by h times x plus h. And now you'll notice that we can cancel out the h in the numerator with the h in the denominator. And we arrive at negative 1 divided by x times x plus h. So we've now simplified this, and we can calculate the limits. So as h tends towards 0, x plus h tends towards x. So this limit evaluates to negative 1 divided by x squared. And that is the first derivative of the function 1 divided by x. Now, our next goal is going to be to calculate the second derivative. So if we want the second derivative, then the definition of the derivative tells us that we take the limit as h goes to 0. And if we take the second derivative, then what we're doing is we're differentiating the first derivative. So we'll get the first derivative evaluated at x plus h minus the first derivative at x divided by h. Now, if you recall, we just calculated the first derivative of this function. It was negative 1 divided by x squared. And we can use that when we calculate the second derivative. So we'll evaluate this function at x plus h. So we'll get negative 1 divided by x plus h squared. Subtract the derivative evaluated at x, so negative 1 divided by x squared. And this is all divided by h. Now once again, we'd like to write this as a single fraction in the numerator. So if we do this, we get negative x squared plus x plus h squared divided by x squared times x plus h squared, and this was all divided by h, so that goes in the denominator. Now you'll see we can simplify the numerator a little. So the quadratic will expand to give an x squared that will cancel with the negative x squared we already have, and the other terms that we'll get are a 2xh plus h squared. and the denominator remains the same. And the only thing left that we can do is we can cancel out a factor of h in both the numerator and the denominator, and we'll be left with 2. We'll be left with 2x plus h divided by x squared, x plus h squared. So now we can evaluate the limit as h goes towards 0. And as h tends towards 0, 2x plus h tends towards 2x. And in the denominator, the x plus h tends towards x, so we'll be left with x to the power of 4. And we can cancel out a factor of x here, so we'll get 2 divided by x cubed. And that is the second derivative of the function 1 divided by x. And we've evaluated it using first principles. So now I will leave you with a few exercises. I've got a few functions that are similar to the function 1 divided by x with some slight adjustments, and I'd like you to calculate the first and second derivatives of each of them using first principles. If you have any questions about these exercises, you can come and talk to me in my office hours, or you can ask questions on Piazza. Thank you.